Okay, my wonderful students, let's begin lecture. Thank you for sitting in the first 7 rows. You are now getting the idea. I'm happy about that. All right, we're going to talk about speeds and acceleration and free fall, and we're going to start talking about the concept of inertia, and we'll get to that and the other 2 laws of Sir Isaac's 3 laws of motion next Tuesday. But before we do that, I have a couple announcements. First of all, the SI schedule is up. And here it is. I'll have this every day in lecture. We'll put it up in web courses and so forth. Shai, do you have a special announcement concerning SI? Please come back here. Okay, speak into that.
Okay.
And also this.
Okay. Can you guys hear me? Yes. Okay. So the SI schedule.
It's Shai's birthday today. Happy birthday to you. Happy birthday to you. Happy birthday, dear Shai. Happy birthday to you. Yay.
Thank you, guys. So as you see, the SI schedule.
Wait a minute. There's got to be somebody else. It's their birthday today. Come on, baby. Who's it? Whose birthday? Dude.
Happy birthday!
Excellent. Stand up. Anybody else? Bueller? Okay. What's your name?
May.
May. May's birthday today too. Okay, so that last one was for you as well, May. Excellent. Good. All right, now you can go.
Okay, so as you can see, 3 of my SI schedules are going to be in a classroom, so that's going to be the same as any SI session. However, the one on Thursday is online. I'll be on campus, and I'll have a webcam, also a mic, and an iPad, and you'll be able to see me, so you can be at home, you can be in the library, wherever you want to be, wherever you feel comfortable. You can view my SI online. I think it starts today, but I haven't gotten my website so that you can access it, as well as the password. So as soon as I have it, I'll post it on discussions, so please look out for that.
Look out for today, you mean?
Yeah.
Later today?
Yeah,
Okay.
exactly. So hopefully before 6 I should do the orientation and then have the website. If I don't, I'll definitely make an announcement saying no online SI session, so you don't have to come. But I'm 80% sure, I'll get to you, that I'll be able to have my online session. And those are permanent unless I say otherwise, so jot those down. They'll be on the PowerPoint every day. I'll have them on discussions. I post them in every SI session, so you won't forget. Did you have a question?
Yeah, I was wondering if the online SIs are going to be recorded so we can watch them later.
Yes, thank you. Great question. She asked if the online sessions are going to be recorded, and yes, they will be. So even if you can't make it, you can go back, or even if you did, just to review for an exam per se, you can go back and watch them again. In the back?
What is an SI?
Oh, that's a great question. I don't really have a lot of time to say it, but I call it a giant review study session. So I'm just there to facilitate it, give you the space. You have your peers come in and you talk about the class, the course, studying, and I try to help you as much as possible. However, I don't give you answers, so we try to do it all together, trying to find the answers. Does that answer your question? Okay. Any other question?
Will all the sessions be recorded or just the online?
Just the online, yeah. Any other questions? Yes. So it's not a review. I will have review sessions before the exam, but those are just SI and review is different, but those are going to be the same every time. So you come in with questions and then we do the problems, or I come in with questions and ask you. Does that answer your question? Okay. Any other questions? Yes.
How do we interact with you on the online ones? Like, do we type up questions or?
Yeah, so that's a good question. So there'll be a chat box, so you can type up if you have a webcam yourself. I won't be able to see you, I don't think, but I can do it where if you are able to say like have an iPad yourself or have like a touchscreen laptop, you can write on the board, the virtual board, and you'll be able to answer questions. I'll post the question up, so it'll be different from the regular SI sessions, but I'll try to make it as regular as possible. So my first online session, I'll probably brief you guys on how to do it. You can speak to me as well if you have one of these, or even if from your laptop, you should have a microphone. Yes, no problem. Yes, I think it should be on there also, but as soon as I get it, I'll post on discussions. So it'll be right on your courses. Any other questions? None? All right, thank you guys.
Okay, thanks, Shai. And I have an announcement concerning the online, and I believe I mentioned this to you before, Shai, and that is for my online physical science class. I do office hours every week, just about using you're using Adobe Connect. Yeah, it's called Adobe Connect. And to answer the question, I think it was Alexi's up here, what do you need? You just need a browser. And if you have, you can use your iPhone earbuds or the built-in mic. The built-in mic really sucks. But if you have, something like this, or a fancy USB headset, or a plug-in headset for a Windows computer, you can actually talk, and it makes things much more efficient. Otherwise, you type stuff in, and it's all recorded really nicely. And if you miss the session, you can go back and review it. And you can't participate, of course, because you weren't there while it was being recorded, but you can benefit from the other students that were there. And you'll see it works really good. It's very good software. It doesn't crash hardly at all. And so it's definitely worth going to. Another thing I want to mention to you before we get down to the physics stuff for today. Last time we talked about subscribing to the highlighters in the bookshelf application, and I forgot how to do it. Darian kind of rescued me and said, yeah, Dr. B, down in the lower left, there's a little icon of a little man with a plus sign next to it, and then you enter the email address. Here's what it looks like. Down here at the bottom, there's the icon. Let me blow it up for you. So this is a little bit bigger. So there's the little person symbol with a plus sign, and you click that, and then you type in the email address of whoever it is that you want to coordinate with and look at their highlighters. So it could be your study partner, or for sure type in mine, and you'll see my lecture or my comments and stuff for many, many places in the text. Okay, so that's how you do that. Questions about that? Yes?
If we do more than one person, will it tell you whose notes they are?
I don't know. You'll have to figure that out. Probably you can. Do you know that?
I'm pretty sure it tells you who they are.
Yeah. So you can subscribe to more than one.
Oh yeah.
Yeah. Okay. So subscribe to mine, and then like a study partner or a roommate or whatever. Okay. And raise your hand if you've got your clicker registered. Boy, that's almost everybody. Now, if you still don't have your clicker, we're going to have some clicking today, but the first official clicking that affects your semester grade is Tuesday. So hopefully you can get, hopefully your financial aid comes in. I know they're kind of expensive, but if you don't have one, you could borrow one from a friend, roommate, housemate, what have you. As long as they're not using it from 10:30 to noon on Tuesdays and Thursdays, you can use it, but you still have to register it through web courses. Okay, so, and And sometimes that works out pretty nicely. Okay, questions about eye clicking? Eye clickers. Happy birthday, dear May. Happy birthday to you. All right. All right. Okay, physics. From homework 3, we had this task. I gave you a table of data that I kind of made up to be the data behind this particular diagram up here. In other words, a strobe photo of a little object slowing down, and you don't really realize it, but this is the final position. So if the strobe kept going, you'd keep getting this dot right here. And I figured out all the equations of motion, and I got everything diagrammed out pretty nicely. And so from x1 all the way down to x, I believe it's x6. And there are 6 places on this, 6 levels on this table. And the question was, the last question was, what are the other average speeds for the other intervals? So that is this question mark, this double question mark, this triple question mark, and this quadruple question mark. So in other words, in one answer, you have to have all of them correct to get the answer correct. And it was multiple choice. Here's how it works. And if you want to jot this down quickly, you certainly can. You're free to do that. Here are the delta t's. It's a strobe. So delta t is set to 1/10 of a second between flashes of the strobe. And therefore, this delta t, the interval between each event, is the same all the way down. So that's the easy part. And for the average speed, that's going to be the denominator. So you're always going to have divide by 0.1. But you still have to figure out delta x. And that is different. So delta x is the difference between 0.27 and 0. All right, the difference between 0.48 and 0.27 and so on. 0.63 and 0.48. And that is found in this column. Now we don't have a list of deltas up here in the first row because you need 2 rows. So I'm parking the delta that describes both rows. I'm parking it in the bottom of the 2 rows. So here's what we have. And those are the delta x's. And by the way, this is the last delta x because according to the equations of motion that I used to generate this, the object would stop at time t equals 0.50 seconds after the 5th flash. It would be at a stop. Now, that doesn't mean the average speeds are 0 down here. But here are the average speeds. And your actual answer was this last 4. And 2.7 was the answer for, I believe, the previous question. So now I may ask you a question like that on an exam. If I do ask you for a question like that on the exam, it would be in the clicker part of the exam. And because of that, I might make this a 4-point question. And you would have to type in 2.1, comma, 1.5, comma, 0.9, comma, and then 0.3, and then hit the send button. And we'll be doing questions like that in the next week or 2 in which you type in numbers and letters. Your iClicker is like a little old-timey cell phone. You know, in the olden days, or the El Cheapo $10 phones that they have now, you don't have like a keypad. You have to, hit like the 3 buttons 4 times, or the 6 button 2 times to get whatever letter you want. Your iClicker works the same way. except you only have one button, the up and down key, select letters and numbers. And I'll show you how it works in a couple days. Probably next week we'll do some numeric and some alphanumeric questions. All right. Now, another question about this, or any questions about this particular homework item? Jordan, you good? Good. All right. Caitlin, you good? Caitlin, where are you? Caitlin, the skateboarder. Where are you at? Ooh, she's cutting class today. Slacking. And she's going to be on the recording. Well. Okay, last time we talked about this pretty close to the end of class. Distance polygon. This is the simplest of all of them, the distance rectangle. And the base times height of this particular polygon formed by the actual velocity graph at the 1 meter per second level, the time axis on the bottom, and then vertical lines left and right end. That tells you the distance of travel. Now, the distance of travel is something that you could put on a graph paper and actually physically draw out a distance or a model of the distance. But this graph itself, a velocity graph like this, velocity versus time, is abstract. But the interpretation of that is that the area is equal to the distance. And it's pretty easy. The base times height, base is 2.5 seconds. The height is 1 meter per second. And you can't really crank those into the Pythagorean theorem and make sense the way it stands. I mean, there's ways to handle it, but for us, the thing to note is that the seconds units cancel, and you're left with meters, and that tells you the interpretation of the area. It's a distance. Okay, in this particular case, 2.5 meters. And that interpretation is basically kosher. Now, if you've ever seen, if you've ever done any computer graphics, you know that to draw or to draw any figure, you have to pixelate it. And the smoother the smaller the pixels on your screen, the smoother a given curve looks like. Now, we can make any velocity graph, even one that's curving up to the right or dipping down on a curve to the right, we can pixelate it and turn it into a zillion little rectangles. It's not a problem. And computer-wise, the guys that are pushing spacecraft to the moon and beyond, all those guys down at Mission Control, that's basically what they do. They just have really fine scale little triangles. And they don't try to draw pictures, but they try to crunch the numbers for it. So this is a pretty basic interpretation of this abstract velocity graph. Before we go to the distance triangle, the other polygon that we talked about last time, I want to give you a couple notes about uniform motion. And that distance rectangle is uniform motion. Constant velocity, meaning constant speed, constant direction. All right? So if you have uniform motion from point A to point B, it could be in a certain direction and a certain speed. And the arrows that you assign to describe each motion, the longer the arrow, the more speed. And so if this is 30, then twice that arrow down here will be 60 kilometers per hour. All right? And then you could also have a different direction, and so you tilt the arrow to whatever direction that you want. So it's a certain number of meters per second. And if it's uniform motion from point A to point B, then that means that you have the same number of meters per second of travel. So delta x over delta t, or delta y over delta t if you're going along the y-axis on your graph paper. It's the same for each. Now you have to also specify the target point, and that means you have to have a direction. And my wonderful students, that is how you construct a velocity. And as I mentioned last time, velocity is a vector. It is a vector quantity. And matter of fact, it's the prototype vector quantity in all of mathematics. It's kind of cool. In other words, for instance, in the theory of relativity, when we think about the curvature of space-time itself around a black hole or during the Big Bang theory or the Big Bang era or something like that, every vector that we draw is basically modeled on a velocity, tangent velocity vector. It's kind of cool the way it works out. And you're learning about them in this class. And so measurement-wise, Galileo said, if you want to talk about something, you got to measure it. If you haven't figured out how to measure it, figure out a way to measure it. All right? And then you can start talking about mathematical structure of the universe. You've got to have measurements of some kind. Okay, so for velocity, it's basically time and distance. And the first chapter of the book goes into a lot of that. How to find your position, how to describe it, how to measure it, and the same with time measurements. There's also a discussion in there, I believe it's in chapter 1, about the tortoise and the hare heading down University Boulevard to Dunkin' Donuts. So that's a good discussion about average and instantaneous speed as well. Okay, uniform motion, and we'll be talking about uniform motion a lot in this class, and we'll be talking about accelerated motion. And so for accelerated motion, you need to talk about the distance triangle. Now this one's a velocity graph, and this one starts out with initial velocity 3 meters per second. Now it's not on the slide, but you can add this to your notes. Go ahead and make an X and a vertical and a horizontal axis. The horizontal axis is the time axis, and our triangle goes out between 0 and 4 seconds. And on the vertical axis, it goes between 0 and 3 meters per second. And if this were a velocity along the x-axis, so left and right across the front of the room perhaps, then positive 3 meters per second would be to the right. Okay? And then if you did have motion to the left, that in this direction, which you can have physically, on the graph you would express it with negative numbers. But this one is only positive numbers. So here you've got something that starts out with 3 meters per second and smoothly loses all of that speed in 4 seconds. All right? The area of this distance polygon is 1/2 base times height. It's a right triangle. It's a right triangle because the time and the velocity axes are perpendicular. And that's by construction. That's by definition. Okay? And the base is 4 seconds. The height is 3 meters per second. Again, these are not commensurable quantities. Or as your mom used to say, you can't mix apples and oranges. It's like a law of the universe. And only moms are allowed to say it. Don't mix apples and oranges. Anyways, don't mix apples and oranges, but you can multiply them together and get a physical meaning to it. It's the distance of travel. Last time we got to this point, what I wanted to do was basically move this factor of 1/2 from the geometric formula and park it underneath here, 3 meters per second divided by 2. Now, mathematically, that is perfectly kosher. But physically, it means something. All right? And what it means is that this quantity has a specific physical meaning. And I asked you to think about that at the end of class last time. Has anybody done any thinking? I know it's a big task. I had a student up here in front say, you know, Dr. B, I was reading the textbook last night. And I thought, what? A student reading the book? Goodness me. All right, so physical meaning. The total speed, 3, initially, divided by 2. Let me ask you a question. What is the final speed of this object? It's 0, yeah. I heard somebody say 0. So write down final speed 0. V subscript F equals 0. And then the initial speed we already talked about. That's 3 meters per second. So what would the average speed be? Final plus initial divided by 2? It'd be exactly this. This is the average speed for the velocity graph. Okay, so make a note of that. This is the average speed. All right, and so this formula is elapsed time, the base, times the average speed. And now we've got a formula that started out as a geometric 1/2 base times height times formula. Now we've got something that looks good. You know, speed times time equals distance. I hope that makes sense to you. Now, here's another thing. Average speed is equal to the acceleration times the elapsed time. So last time we discussed the fact that acceleration is the quotient of delta V and delta T, the change in the speed or the change in velocity divided by the elapsed time delta T. And this numerator here, A delta T, is equal to, and divided by 2 is the average speed. Okay, so the amount of speed you gain or that you lose divided by 2, that's the average speed as well. So now we can put that into the equation. Here's delta t, here's average speed, and average speed is A delta t over 2. So now we have delta t over here and A delta t over 2 right here. All right? And we're kind of putting things together in a particular way for a smoothly accelerating object. Actually, I should say a smoothly decelerating object. And the result is that the distance is this fairly simple formula. Distance equals 1/2 times the acceleration, whatever that is, times the square of the time. Or you could write it as the square of delta t. So delta t in parentheses, quantity squared. A lot of times we'll just use it this way, 1/2 a t squared. And that is the general formula for distance traveled by something that is accelerating. The distance that you acquire or lose because of your acceleration. Now, we also have the distance rectangle. So things can get a little bit complicated. We're going to start putting that together. Here's your general principle. And that's a distance triangle formula for some general acceleration. By the way, what's the rise over run for this blue triangle? Rise over run. Is the rise equal to 3? No, the rise is -3 because it's dipping downward to the right. So the rise is -3, and what's the run? 4. So the acceleration here is -3/4 meter per second per second. Go ahead and write that down. In this diagram, A equals -3/4 meter per second per second. And what that means is for every second of acceleration, you lose 3/4 of a meter per second of speed. Right? So here at I don't have the 1 second mark, but it's right about here. You've lost 0.75 of the original 3. So here you're at 2.25. That's right about here. All right. At 2 seconds, 0.75 negative times 2, that'd be -1.5. You've lost about half your speed. That's right in here. All right. So your speed is supposed to be 1.5 meters per second. And your final speed over here is, of course, 0. You start with 3, and in 4 seconds, you've lost all of it. You're now down to 0. And you've stopped, at least for an instant of time. Variation, vertical, drop distance. And for something falling from a height, the distance of free fall is generated from this. The symbol that we use for the acceleration due to gravity is little g. And we'll work with this in just a second. Okay? And so the question then is, how do I set up a distance triangle for something that's falling? If you're on top of the library, or actually on top of this building is pretty tall as well, and you have like a water balloon or a penny or a baseball that you want to drop off the edge of the building, you know, we're about 10, 15 meters at least to the top of this building. The library is even taller. Okay, it's going to take some time for it to accelerate and hit the ground. And so you start out at the top of the library, the top of the classroom two building, and the initial speed is 0. And eventually it's going to have a negative downward speed, all right? And so let's set up the time scales here. Let's do 2 seconds of horizontal scale. And let's do 2 seconds of free fall. Now, in the metric system, the acceleration due to gravity is 9.8 meters per second per second. And it's downward. Let me repeat that. In the metric system, g is equal to 9.8 meters per second per second. Its direction is downward. So we might want to put a minus sign on that. But usually it's written as g equals 9.8 meters per second. Or, hey, you guys, you can write it out this way. G equals 9.8 meters per second squared. A little more compact notation. All right. So here are our axes horizontally. Here's your initial, this red dot here where I have the cursor. That's your initial position on the graph. You start at the top of the library. You're holding it. And when somebody says go, you drop it. And that instant that you let it go, its initial speed is 0. In 1 second, it acquires 9.8 meters per second of downward speed. So go down here into the negatives and just put a mark down there, and we're going to label it as 9.8 meters per second negative. All right, so that's going to be right here. All right, so at 1 second, so right below 1 second, and right across from negative 9.8. And make another mark over here. Same distance again, downward. And that's going to be negative 19.6. And now you, after 2 seconds, you've acquired another 9.8 meters per second downward. So another negative 9.8 meters per second of speed, or I should say of velocity. And so that's after 2 seconds. So that's right down here where the second, actually that's the third red circle. And go ahead and draw a line through that. There's your velocity graph. Assuming that the baseball you drop off the edge of the library accelerates smoothly, which it pretty much does. There's a little bit of air resistance, but we'll forget. If you're a baseball player, you have to keep air resistance in mind because that's one of the things that makes a curveball curve. But for most things you can neglect. Most things that you can do with a baseball or a football or something, you can neglect air resistance. Okay, here's your area. There's your area, there's your polygon for which we want to compute the area. And I made this one gold colored. And so the drop distance, so you drop that water balloon from the top of the library, figure out this, and if it lands 2 seconds later, this is the distance that it fell, right? 1/2 GT squared. So that's how that works. And we're going to do an example with that together in just a few minutes and do a calculation together from the Fellowship of the Rings, Frodo and Samwise and all those guys. And but before we do that, I want to talk about Galileo and Aristotle. Aristotle said this about motion. Each thing that exists by nature has within itself a principle of motion and of stationariness in respect of place, or of growth and decrease, or by way of alteration. That's a typical sentence from Aristotle. Now, when he said alteration, he was like saying that a plant grows. That's kind of a motion. Growth and decrease by way of any kind of alteration. For him was motion. But what Galileo did was he simplified it. He simplified it to meter stick and pendulum motion. So make a note of that. For Galileo, motion was something that you measure with a meter stick and a pendulum or other clock. He invented the pendulum clock, and he developed a water clock to measure time. He never perfected the pendulum clock, but somebody soon after he died did actually make one. Galileo designed one, and somebody else made the first one, I think up in Holland. Anyways, he restricted his view of motion that he wanted to study to be meter stick motion. He wasn't saying there's nothing interesting about the way plants grow or the way Aristotle, he had this enormous concept of motion. And for instance, the two cities of Greece, the two classic cities of Greece, Athens and Sparta, famous for having gone to war against each other at various times. Did I say gone to war? Yes. And Aristotle considered that a form of motion that he had to study. And in a way it is. You're going from one state to another state, from a state of peace to a state of war, but you can't measure that with a meter stick. That's a great sentence. Athens and Sparta go to war. They go from a state of peace to a state of war. But you cannot measure that distance with a meter stick. And therefore Galileo said, I don't care too much about that. Hopefully we stay in a state of peace, but I'm trying to figure out where something is going. I'm going to stick to a more restricted view of motion, meter sticks and pendulums and other clock devices. So let's look at what Galileo learned. This is from a famous book that he wrote when he was 70 years old, The Dialogue Concerning Two New Sciences. The properties belonging to uniform motion, you don't have to copy this, you can look it up on the internet. Just look up The Dialogue of Two New Sciences. The properties belonging to uniform motion have been discussed in the preceding section, but accelerated motion remains to be considered. Next paragraph. And first of all, it seems desirable to find and explain a definition best fitting natural phenomena. That is what Galileo wanted to do. He said if it doesn't fit natural phenomena, the book, this grand book of the universe, constantly open to our gaze, he said we're not going to talk about it. Anyone may invent an arbitrary type of motion and discuss its properties. Thus, for instance, some have imagined helices and conchoids as described by certain motions which are not met with in nature and have very commendably established the property which these curves possess. And those are two curves, a helix and a conchoid. We find them in nature. They're not easy to find. A helix, of course, is the structure of the DNA molecule. And Galileo invented the telescope, but not the microscope. And even the best optical microscope, you can't see DNA's helix. We'll figure out different ways. We'll talk about ways of seeing the DNA helix. But anyways, so there's, as it says, they very commendably established the properties of these deluxe curves that they possess in virtue of their definitions. But we have decided to consider the phenomena of bodies falling with an acceleration such as actually occurs in nature, and to make this definition of accelerated motion exhibit the essential features of observed accelerated motion. This was the key thing that he did. This is his big breakthrough, one of his big breakthroughs. He said that we're not going to figure out some fancy spiral or some conchoid shell-shaped curve. We're just going to do straight up and down vertical free fall. And he said, I'm going to assume, just like the velocity rectangle allows you to figure out by pixelation any curve, a triangle as well as a non-polygon shape. He said, I'm going to make this simple acceleration the prototype of all accelerations, even something that's for which the acceleration is changing. I can relate all of it back to the simple free fall acceleration. Huge strategy move on the part of Galileo. And I'll continue. And this at last, after repeated efforts, we trust we have succeeded in doing. In this belief, here we go, we are confirmed mainly by the consideration that experimental results are seen to agree with and exactly correspond with these properties which have been one after another demonstrated by us. In other words, he said, ding, I have experimental verification of this. He did and we're going to talk about his experiments. There's the famous experiment that he did, they say, from the Leaning Tower of Pisa. He dropped two different weights from the top, and they both fell at just about the same amount of time. Finally, in the investigation of naturally accelerated motion, we were led by hand, as it were, in following the habit and custom of nature herself, in all her various other processes, to employ only those means which are most common, simple, and easy. Go ahead and type in that word. Only those processes which are most common, simple, and easy. And next to that, in parentheses, write the phrase, Galileo was a slacker. And scientists in general are slackers in a similar way. In other words, we want to find the explanation that is most simple. And the complicated, like Aristotle's stuff was extremely complicated. And we're going to try, Galileo is saying we're going to try to keep things physical, experimental, and as simple as we can do. And he was very successful with it. Our whole scientific enterprise of this day, 400 years later, is based on these kind of decisions that he described in this book. All right, and here are the pull quotes for that. So you can jot those down a little bit. And Galileo, you know what's interesting about Galileo? He was actually he started out as a professor of mathematics. And he invented physics. I mean, there were guys that, were kind of trying to figure out pendulums, trying to figure out water and why things float and sink. But he's the guy that set all of it in place by this kind of discussion and these kind of ideas. So he's basically, if you think about this university, we are descended from Galileo, from his university. 400 years later, we're like the great-great-grandcestor, or he's like our great-great-grandcestor. We're part of his tradition. He is the headmaster, and I'm a pupil of his, and so are you guys. And we're all following in his footsteps and trying to master what he started. From the Leaning Tower of Pisa. I observe a stone initially at rest, just like we just talked about, the drop triangle, the drop distance triangle. I observe a stone initially at rest falling from an elevated position, continually acquiring new increments of speed. And so what that means is every second, every tenth of a second, every flash of the strobe, whatever you set the strobe setting to be, if you could measure the speed, it's going to be more and more. And always the same amount is added. If it's free fall, if it's a simple, smooth, accelerated motion. Now, the skateboards going down the aisle were pretty smooth, and we could measure the acceleration, but it would not be truly uniform. Basically because you can change your weight distribution and maybe slow down a little bit. You can swerve a little bit, left to right as you go down the aisle. So the acceleration is not constant. But free fall is pretty good. If we now examine the matter carefully and we find no addition or increment more simple than that which repeats itself always in the same manner. So there's your pull phrase from this part of our Galileo discussion. The acceleration adds velocity and repeats itself if it's free fall, simple free fall, always in the same manner. It's repetitious. So it would be like a Leaning Tower of Pisa, and if he said, okay, I'll drop the two weights and start my stopwatch and measure the speed, it would be like this. After 1 second of free fall, here's this downward speed, 9.8. Now I'm leaving the minus signs out here. Excuse me. Oh boy. 2 seconds. Always the same increment, repeating itself always in the same manner. So after 2 seconds, another 9.8, total 19.6. 3 seconds, dun, 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 another 9.8, total 29.4. What's the downward speed going to be at t equals 4 seconds? Do you have your calculator? You better get them out. Get your calculator out. Get your iClicker. We're about to do an iClicker question. We're going to do a distance triangle calculation. Four seconds. What do you think? Raise your hand. What do you think it's going to be? I see a hand back there. I see one up here. Anybody over here? 4 seconds. What do you think it's going to be? Raise your hand if you I see you. I see you. Okay. Over there on the aisle. What do you got over here? All the way over on the right. 39.2. 39.2? What? 4 times 9.8. Yeah, 39.2. And etc. You know, depending on how tall. You know, you might crash in the ground after 4 seconds. That's pretty tall building. 4 seconds. You know, I wonder how long it takes something, you know, like a BB. No, you wouldn't want to drop a BB off the Empire State Building. I mean, because if somebody's on the sidewalk, it'll totally crush their, you know, it'll go right through there. You could probably kill them. But if you did it like at the middle of the night, in the middle of the night, you could probably do it. You know, like from the 86th floor of the Empire State Building. And make a side note here, the direction is downward. I left the minus signs off here. So as we say, in the metric system, which Galileo wasn't using the metric system, I don't even want to think about what system they were using in Italy. But they probably had some distance system. But the idea is the increase repeats itself. Always another 9.8 meters per second of downward speed for every 1 second between strobe flashes. Now, if you have a different strobe set to every 0.2 seconds, you have a slightly different table. But those times will be in the table, you know, somewhere in it. You just have more intervals to think about. So free fall acceleration on the surface of the Earth, usually symbolized with the lowercase g, 9.8 meters per second, or more compactly, 9.8 meters per second squared. Now we're going to do a calculation next from the Mines of Moria and the Fellowship of the Ring and the time of maximum danger for Gandalf. And why was it a time of maximum danger? Well, because of this fool, Peregrine Took. And he dropped something into the Mines of Moria, and all hell broke loose after that. All right, so here we go. I'll go ahead and jot this down. We drop a rock down a well, and we hear a splash at 3.2 seconds. How deep is the well? Right now, the Mines of Moria were a lot deeper than 3.2 seconds worth of free fall. But let's do something with a nice round number. Let's see if we can figure it out. Okay. And what we're going to do is figure out how far the rock falls in 3.2 seconds. Now, this is the drop distance formula. It's not a formula for position per se, but it is a formula for just getting how far something is away from you. You know it's downward. That's good enough. You know, how far away is it? So here's the numbers when you plug them in. 0.5 for 1/2. And then 9.8 meters per second squared for G. And notice that I don't have a minus sign in here. Eventually we're going to put a minus sign in there when we try to keep track of high and low, side to side in 2 dimensions. But for now, just a straight drop. Good old 9.8 meters per second squared for G is good enough. And then T squared, or delta T, quantity squared. 3.2 seconds, quantity squared. Now make sure you put brackets or parentheses around 3.2 seconds and that you square it outside the brackets, outside the parentheses, so up here to the left. All right? Now you got to square that. So take your calculator out. What's 3.2 quantity squared? It's going to be bigger than 9, so what is it, 9 point? What do you got? Okay, anybody else verify that, 10.24? Okay. All right, so here's our calculation. And hey, you guys, by the way, I put 0.5 and 9.8 together for a 4.9 meters per second squared. But I haven't done any cancellation yet. But you can cancel second squared in the denominator here and second squared up here in the numerator and cancel those babies out. And the only thing that's left is meters right over here. And that's good because you want to have a distance unit in your answer. All right? So now you multiply those two numbers together. 4.9 times 10.24. Who's got it? Raise your hand if you got it. Let's see. Who's got it? Okay, way back there. Don't look back. Yeah, you. Yeah. 50.18. Well, yeah, that's pretty good. 50.176. And round it off to 50.18, yeah, meters. So that's pretty deep. All right. That's like, that's taller than the library. You know. Question?
Yes, when we're doing these calculations, for example, on homework and things, do you want us to round off to the...
On a problem for which you have to type in an answer, a calculation, I'll always specify where I want you to round it off. Whether to 2 decimal points or 1 or 0 decimal points, whole number, you know, I'll specify that. So don't worry about that ahead of time. You'll see it when you need it. And the same on exams, I'll specify that, how to round stuff off to the nearest whatever I want on the test. All right, so now get your clickers ready because I have a clicker question for you. Multiple choice. And I want you to try to calculate this one. Hopefully you took notes on this calculation because the next calculation is going to be, we're on frequency BB. And here's your question. Your dog's treat drops for 2.5 seconds in the mines of Ocala. What is the drop distance? Look at this dog. This is on Reddit last night. So I said, I got to use that in class somehow. Okay, 30 seconds. This is kind of a calculation question, but you've got all the answers in there. So, and if you don't have your clicker with you today, make sure you jot the questions down and at least put them in your notes. And next Tuesday, you definitely want to have your clicker ready. Five, 4, 3, 2, 1, 0. Okay, let's see what you guys have got here. Dr. Brickner. Yeah. Is G always 9.8 meters per second squared? Yeah. G is always, at the surface of Earth, G is 9.8. Now, if you go up to like the altitude of the space shuttle and the space station, the gravity's acceleration up there is a little bit smaller because it's further away from the Earth. But if you're anywhere from the top of Mount Everest to the bottom of the Mariana Trench, the deep blue sea, it's 9.8 is pretty good. And we can measure variations of it. If you are right next to Mount Everest, that's a huge pile of rock, extra mass. It'll vary the strength of G towards the mountain. So that'll change things a little bit. We can measure that. It's a pretty small effect. All right. Well, let's see. It looks like you guys did pretty good. The answer is B, 30.625. And I am very happy about that. You guys did good with that. Because you're going to have some homework with that. So let's dismiss. Your homework will be available by lunchtime tomorrow, and it will be due on Tuesday, 10:30 a.m. You're dismissed. See you next week. Diagnostic
Yeah,
test?
like something on web courses, it comes up for this class and it's like diagnostic.